All right, so we're going to start off with a multiple choice problem here. So we have a situation with an Atwood machine, two boxes connected by a rope over initially a massless pulley. And so the problem tells us that the tension in the rope connected to the left box is going to be T1, and then we have the force of gravity acting on that box. I'll call that FG1. And the tension in the right rope is going to be T2, and we have the force of gravity acting on that box, FG2. Okay, now our system is going to be accelerating, so that box 1 is accelerating up and box 2 is accelerating down. I'm going to go ahead and write my F equals ma for each of these boxes, all right, because that ultimately I think is going to help me figure out this problem. So I'm going to say for box 1, T1 minus FG1 equals ma, and for box 2, I'm going to say that FG2 minus T2 equals 2ma. Okay? Now, what I'm going to think about is when we add mass. Okay, so when that pulley has mass, what does that do to our system? And the key is when we add mass, the acceleration of the system will decrease because we don't ultimately have any new forces acting on the system. Okay, it's still really FG1 and FG2 as the outside forces that are accelerating the object, and those don't change. What does change, though, is the total mass that needs to be accelerated, because now we need to provide an angular acceleration for the pulley. So keeping in mind that our acceleration will decrease, let's think about how that affects these two forces. Well, if our acceleration decreases, if we look at this equation, FG1 doesn't change. So the only way for that to happen is if T1 decreases. Okay, and for FG2, all right, if our acceleration is going to decrease, the only way for that to happen is if T2 increases, because, okay, FG2 is going to remain the same. So to have a smaller acceleration, we need a bigger force opposing that force of gravity. So that ultimately means that the left rope will increase while the right rope will decrease. Okay, so moving on to the next problem here. We're starting with the wheel at the top of a ramp, rolling down this ramp. We do have friction between the wheel and the ramp, and the wheel is going to roll smoothly. So we want to start by drawing all the forces acting on the ramp, and as always with these torque ones, indicating where those forces act. So first force we have, the easiest one, is gravity acting from the center of the object. We have the normal force acting at that point of contact. I drew it a little bit off, but at that point of contact, going up. And we're also going to have friction. So the wheel is going to be rolling to the left down the ramp, which means it's ultimately going to be rotating counterclockwise. And so we need some force causing that rotation. And in this case, it's going to be the force of friction going back up the ramp. So what force causes the wheel to accelerate angularly? That is going to be friction. C, we want to derive an expression for the acceleration of the wheel in terms of theta, r, f, and fundamental constants. So this is a situation where we have an object that is accelerating angularly and is accelerating linearly. So we're going to set up some of the forces equals ma and some of the torques equals I alpha. Let's start with the forces here, and really we're thinking about the forces in the x direction. So what forces do we have in the x? We have our force of friction, and we also have gravity. Remember, when we deal with inclines, we typically take that gravitational force, and we're going to break it up into its x and y components. So there's our angle theta. So we're going to have Fg cosine of theta as our y component, Fg sine of theta as our x. So that hasn't changed. So in the x direction, we have that Fg sine of theta force minus the force of friction, and that's going to be equal to our mass times our acceleration in the x direction. Normally we'd substitute in with the coefficient of friction, but we don't know that, and actually, as you'll see in a second when we set up our torque equation, we don't actually want that. In terms of our torques, okay, we know that the only force creating a torque is friction, so we're going to say the torque from friction is going to be equal to I, which in this case is going to be mr squared for the wheel times our angular acceleration. Now, we can substitute in two very important things. The first is that torque from friction is going to be R times the force from friction, times sine of theta, and that's going to be equal to mr squared. And the second thing we can substitute in is remembering that a is equal to r alpha. We know our angular acceleration is simply going to be a over r. So remember, that again is going to be the relationship between the linear acceleration of the wheel as a whole, the translational, in relation to the angular acceleration. We can do a little bit of canceling here. We cancel an r, one r with that r on the bottom, and another r with the r on the other side. We know our angle too is going to be 90 degrees for friction. So what we're left with is FF is simply going to be equal to MA. Okay, so these are our two equations, and we're going to take these and we're going to combine them in order to solve for our acceleration down the ramp. So when we combine them, we end up getting FG sine of our angle here minus MA is equal to MA. So I'm going to add MA to both sides, and I'm also going to substitute in for FG. I know that's going to be MG. So MG sine of theta is equal to 2MA. My M's cancel, and I find that my acceleration is simply G sine of theta divided by 2. Okay, for the last one, it's just a conceptual question here. We want to know what would happen if a substance was put on the incline so that it became frictionless, and what would happen is it wouldn't roll down the ramp. Okay, we would no longer have that frictional force, which ultimately led to the torque over here. Okay, and so it wouldn't roll; it would simply slide down the ramp instead. And we actually could find the acceleration. We could simply take this expression and get rid of that force of friction, so it would be mg sine of theta equals ma. So our acceleration would just be g sine of theta. So that last part wasn't really necessary, but we could find the acceleration. It'd be no different than an object sliding frictionlessly down the ramp. For this next problem, we have an Atwood machine with two boxes connected via a rope over a pulley that is frictionless. And so I'm going to start out by simply just identifying the forces we have in this situation. That's always a good place to start. So in this box, this is object 2, so I'm going to call this FG2, and we have a force of tension going up on that box. On the other box, we're going to have a force of tension going up, and we're going to have FG1. And the forces then on the pulley, we're going to have a force of tension where at each point where that rope connects to the pulley. We also have the force of gravity on the pulley if it does have mass, and we'll deal with that idea in a second, and the force from the axle or the normal force, whatever you want to call it. Of course, those ones we don't care about as much because they act on the pivot. So to answer our first question, if the pulley is massless, will the force of tension acting on box 1 be greater than, less than, or equal to the force of tension acting on box 2? And the answer here is they're going to be equal. Okay, and the reason is since the pulley is massless, there will be no net torque on the pulley. The only two forces creating a torque are T1 and T2, the two tensions. Okay, so let's actually go ahead and label those. So T2, T1 here. So those tensions will be equal if the pulley is massless because no net torque is needed to accelerate a massless pulley. Now, the second question we're considering the case where the pulley does have mass. We want to know if the force of tension acting on box 1 will be greater than, less than, or equal to the force of tension acting on box 2. Now that the pulley does have mass, all right, and keep it in mind that box 1 is going to accelerate down while box 2 accelerates up, which means the pulley will have an angular acceleration in the clockwise direction. That means that FT1 must be greater than FT2. And the reason for that is we need to create a net torque in the clockwise direction. And therefore, FT1, which is creating a clockwise torque, must be a bigger force, so it creates more torque than FT2, which is creating a counterclockwise torque. For the last part, we want to derive an expression for the acceleration of the system in terms of m and fundamental constants, assuming the pulley has a mass of m and is shaped like a cylinder. So we're going to go ahead and set up the F equals ma for the forces on each object. We already have our free body diagram, so this should be relatively easy. and then of course we're going to do the torques on the pulley. So for object 1, which is the box 1 over here, it's going to be Fg1 minus the force of tension 1, and that's going to be equal to 2ma. We switch here to box 2, and that F equals ma is going to be Ft2 minus Fg2 is equal to ma. And of course we are going ahead and making acceleration be the positive direction. And then we can do our torque equation, and that is going to be the torque from force 1, which is going in the clockwise direction, minus the torque from tension 2, which is going in the counterclockwise direction, is going to be equal to I alpha. We can make a few substitutions here. So for Fg, I can plug in mg. So this is going to be 2mg minus Ft1 equals 2ma. This next equation is going to be Ft2 minus mg equals ma. And then we can plug in a lot of things here into our torque equation. We're going to keep in mind that torque is Rf sine theta, so that's the first thing I'm going to sub in. Our moment of inertia for a solid cylinder is 1/2 mr squared. That's the second thing. And we can link angular acceleration and acceleration by saying R alpha equals our linear acceleration. So our angular acceleration is going to be the linear acceleration of the boxes divided by R. And that just results in the fact that the boxes and the rope are accelerating at the same rate, and that rope runs along the outside of the pulley here, so the tangential acceleration of the rope, which is the acceleration of the boxes, is linked to the angular acceleration of the pulley by R alpha. So I can go ahead and make those substitutions. So I'm going to have R times Ft1 sine 90 minus R times Ft2 sine 90 equals 1/2 mr squared times a over r. All right, a lot going on there, but a lot of things are going to cancel out. The sine 90s just are 1. One of the r's here cancels out with the r squared because it's r divided by r, and now we have an r in every single term, and so all of those go away. And this equation simplifies pretty nicely to Ft1 minus Ft2 equals 1/2 ma. I can solve for Ft1 and Ft2, so I can say that Ft1 is going to be equal to 2mg minus 2ma. I can say that Ft2 is going to be equal to ma plus mg, and then I can substitute those in and make one big equation here. So bringing all those equations together, I get 2mg minus 2ma, that was just Ft1, minus the quantity ma plus mg, which is just Ft2, equals 1/2 ma. Distributing that negative sign, I get 2mg minus 2ma minus ma minus mg equals 1/2 ma. The mass terms here cancel out, actually, so I can get rid of all those mass terms. And I'm going to move all the a's then over to the right side, and I'm going to be able to subtract 2g minus g. So the left side of the equation, all I have left with is g, and I'm going to add all those a's on the other side, so I have 1/2 a plus 2a plus 1a, so I end up getting 3.5 or 7/2 a, and that means that my acceleration here is just going to be g over 3.5, which works out quite nicely there.